Hello everyone and welcome to another AP Computer Science video. In this video we're going to continue with our relational operators and logical operators and the combination of them, because we can make complex Boolean statements that evaluate many different facts together and result in one final Boolean value. And as we move forward, we're going to see this becomes more and more valuable to our programming. So the first thing I want to talk about in this video is comparing non-numeric values, in particular char values, single character values. And everything we've done so far has been ints. We could use doubles. It's pretty arbitrarily easy to include doubles in our comparisons. But there is one aspect of doubles that we'll discuss as well that's important to recognize. And so what we're going to do is first focus on characters. So let's make some char variables. We're going to say char. And we'll go ahead and put the letter A. And we'll make another one. I'll put the letter B. So we can also compare single characters against one another just as if they were numbers. And when it comes to equality, it's pretty easy, right? Either the two characters are the same or they're not. That's a pretty obvious one. But when it comes to greater than and less than, or greater than or equal to, then we have to know a little bit more. And we can still do it, and it is useful. We have to make sure we're clear on how they're actually interpreted by the system. So let's make a Boolean variable. And we'll call it comp for compare, and we'll say first not equal to second. And if we print this out, hopefully we recognize that we should see true, because a, the lowercase a, is not equal to the lowercase b. So let's go ahead and run it and let's see what happens. We should get, our last thing should be true. And there it is, that last one is true. And if we made this equal to, then it would be false because they are not the same thing. And there it is as false, right? So we're comparing individual characters. Now, what would make this more interesting is if we did a capital A. Is a lowercase a equal to a capital A? And again, as human beings, we kind of can make a decision easily, or at least think in our minds, well, if we consider only content, then yes, they're both the letter A. But if we're being very strict, then no, they're not, because one is capital and one isn't. And so Java doesn't do that. It's making a very clear, easy decision. If they're not the same character exactly, then they're not equal. And so this will be false because a capital is not the same as a lowercase value. They are distinct. The case of characters matters, and there's a lot of situations in many programs, if you think about it, that matters, right? Passwords, capitalization matters, symbols matter. Usernames, sometimes capitalization matters. Emails, capitalization doesn't matter. Sometimes you can put capital letters and it still works. Sometimes you can mix and match and there's no problem. It really depends on the system. But in the Java programming language, the capitalization means distinct char values. And so that's not such a big deal with equality and not equal to, but when it comes to comparing things, for example, greater than. If I said comp is equal to first greater than second, that might seem very strange, and for us to know the answer, we have to kind of remember that Unicode table that we had looked at before when we were looking at the char values. Right, so the actual comparison is very simple. It's essentially comparing numbers behind the scenes. Every character of value that exists in the Unicode table has a numeric equivalent. And so if we were to open up that Unicode table, and I'll go ahead and do that, we would see the chart. And if we look, we can see the capital letters A to Z, and we can see the lowercase letters A to Z. And so this actually suggests that capital letters are smaller than lowercase letters. So in the question of is first greater than second, it's true. And if we actually look at the numeric values, if I click on the capital A, the HTML code number 65, that's also its decimal equivalent. So capital A is the same as the number 65. The lowercase a is the number 97. So is 97 greater than 65? And the answer is yes. So we expect to see true. And so we can go ahead and run this, and we should see true as our final answer. And there it is, right? And so what we're saying is that it's not about what letters we mean. Is a Z more important than an A? It's not really because it goes in that order. It's mainly because of whatever order this happened to put. Because that means that we could compare more exotic symbols. So for example, if I compared a capital E against a backslash, then the capital E is smaller than the backslash because it comes before backslash in the Unicode table. And so if we went to the more exotic symbols that are not just standard English letters, then those would all be larger than all the English alphabet. And so it's really just a matter of where they are in the Unicode table. We can use that to our advantage. And so if we're looking at just capital letters, this is great for sorting them, putting things in order. We know who belongs where because we can say, oh, this letter is larger than that letter. Oh, it is smaller than the other letter. And so same with capitalization and other ones. And of course, the symbols also have an impact, right? A question mark is quote unquote smaller than the capital C, whatever that means, right? Smaller means before in the Unicode table. It doesn't mean size, right? That's a very difficult kind of discussion to have. It's just we have to kind of accept that whatever order they're in, that's how we determine this. So let's go ahead and do one last try. Let's go ahead and say first less than or equal to let's do C or greater than, let's do now this might seem odd, and I'm kind of being very sneaky in what I'm doing. And so I think it's kind of, just to be clear about the reality that the actual language itself doesn't see a difference, and this is not something I would normally do, but I want to point it out, is that the first comparison is a pretty reasonable comparison, right? Is the character first less than the character C? And that's a true or false. Now here, I'm doing something very strange. This comparison may seem odd. 7 times 23 greater than the letter C. I just said that the letter C has a numeric equivalent. So essentially, we're comparing a number versus a number. 7 times 23. 7 times 3 is 21. We have a 1. 7 times 2 is 14. So 161, I believe. Is 161 greater than the letter C? Well, let's look at the letter C. What value does the lowercase c have? In this case, it's 99. So that should be true, right? And so that may seem strange, but the answer, so this is going to be something or true. Now, if we look at the first one, first is the letter A. Is A less than the lowercase c? And the answer is yes. It comes before. Its value is 97. Is 97 less than 99? The answer is yes. So true or true is true. So we should see true as our final print. And there it is, right? And so, I mean, this is not such a common thing. Sometimes it makes sense to compare numbers against letters if we happen to know what kind of symbols are happening. But generally speaking, this doesn't happen. I just want to prove that the comparison of chars is essentially the same as the comparison of numbers. Now, the other thing I want to discuss is with doubles. And there's a danger in very specific scenarios where, and I don't know if I'm going to get it to be able to happen, but we have to be very careful with this idea. And this is a comparison of equality with doubles. The reality is floating point numbers are not always stored the same way internally while a program is running across all systems. The number 1 might not be actually stored as 1.0. It might be stored as 0.999 up to 17 significant figures, or 1.000000 and then a 1 at the very end. And if we were being very picky, we could say nope, they're not the same thing. But in terms of the computer and how they're expressed, they might be the same thing because at a certain point with our significant figures, they're equivalent. And so that's something that we have to be very aware of. So when we do comparisons of doubles, with less than or greater than is not a big deal. I mean, there's a certain accuracy that we're going to get, but equality and not being equal, it was a very dangerous thing. So let's try and see if we can make this happen as an example. So actually, before I do that, I just want to go ahead and put notes. Real quick, we can compare it's just like numeric values, all equivalent. And so we use that to make comparisons. So let's try it with doubles, and let's go ahead and say double D1 is equal to, let's go ahead and say 1.0, and let's do double D2 is equal to 1.0. And then now let's go ahead and say comp is equal to D1 equal to D2. And then let's print out comp. Hopefully we would like to see true as our final result. And there it is, and it seems to be correct. And And let's go ahead and try maybe playing around with this. Let's do something like D1 is a bunch of 9s. I don't know, I didn't count how many, but let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's do one more. 17. Let's see if it makes them equal to each other. And notice they are equal to each other. Let me get rid of a few 9s. So I got rid of 3 9s. Ah, they're not equal. But if you put enough 9s, in fact, 17 significant figures. So this is, I think this is 16. And now suddenly they're the same. Now again, some people would argue, yes, they are the same. They're essentially the same. But the point is that since we cannot guarantee how a... oh, actually, let's try something even more strange. I wonder if this will happen. So 1.0, and how about like this? Oh, now we're getting kind of off. So now, is the argument that we're 0.00002 away different? Is that enough to say the different numbers? And so the reality is that we can't control it. So we have to be very careful when it comes to comparisons. Instead of taking this approach, we take a safer approach. We say, you know what? Let's have some kind of error that's acceptable to us. And if we're that close, then we consider them equal. So for example, in one system, a difference of 1/10 might be enough to consider them equal. And that's a pretty big difference. In another one, you might want 1/1,000,000th to be the difference to be equal. If you're within 1/1,000,000th of each other, then you're the same. If you're within 1/10th of each other, then you're the same. So depending on how aggressive we want to be in our determination of equality, we could do that. But that requires us to do a little bit of math. So let's go ahead and say how we might calculate this. So if we have two numbers, we're going to add a third number. And we're going to call it error, right? So I'm going to call it ERR. And we'll say that the error is a number that we pre-choose. We're going to say, you know what? That if you're within, and this is what? Let's count. A tenth, hundredth, a thousandth, a 10,000th, a 100,000th, a millionth of a decimal point between the two numbers. If that's how different you are, then you're equal to each other. If you're larger than that, then you're not equal to each other. And so how would we compare numbers? Instead of saying equal, we would say comp is equal to the absolute value, because we don't know necessarily who's positive, who's negative, potentially, or what order we're subtracting in, so the absolute value, my computer is, I think I might have frozen NetBeans. Let's give it one moment. There he goes, that was weird. The absolute value of the difference between the two. So D1 minus D2, right? And so the comparison is that less than the error. If that's less than the error, then we are equal. So if it's true, if this number is smaller than this one, the difference is less than a millionth of a difference, and therefore we consider them equal. If it's a larger number, then that means they're not close enough, and therefore we consider them not equal to each other. So if we printed this, and we said, let's do system. Oh, let's print out comp. And so now the question is, are they within that close range? I think that they are, so we should see true, hopefully, as an answer. And there it is. And now let's go ahead and make this a lot smaller. Let's actually do this. Actually, let's do this a lot. Let's change the numbers. So let's put one at 0.9999. Oops, too many dots. And then one at 105. Are they equal to each other? The answer is no. Because if you subtract the two, and I'm just going to use it. I'm going to do it using a calculator, just so we can see the exact number. 0.9, so 5 9s, is 05001. That is not smaller than our error. Our error is 1 million. This is basically 5 hundredths, or 5,001. What hundreds, thousands, 100,000ths of a difference, and that means that they're not equal to each other. So this is kind of an arbitrary thing, but it allows us as the programmer to decide what is equality. Because unfortunately, if we trust the computer, one day it might say true and one day it might say false, and we do not know how certain values are expressed, right? Because one time the 1.05 might be expressed as 1.05, another time it might be expressed as 1.0499999, and so on. And so instead we take the approach of make a comparison And if it's within some error bound that we agree to, then we consider them equal. That's the better approach for comparing doubles. And we'll come back to this concept later on and use it in a more meaningful way, but the idea is that we should always have this on our mind when it comes to equality between doubles. It's not so easy, unfortunately, as comparing with the equal symbol. So let's go ahead and say use instead of using the equality comparison. So there it is, right? So again, we use the error-bound concept instead of the equality comparison, and again, we get to choose how close the numbers need to be equal to each other, and it stops us from having to worry about the internal representations of floating point numbers, which we don't typically have control over or even aware of most of the time. So this is a better approach. Okay, so I'm going to make a new file and continue with our logic operators. So this is all relational operators, and these are pretty good concepts, but let's finish this up and do our logical operators. So I'm going to make a new class, and I'm going to call this one De Morgan's Law. And this is a very specific idea in logic, and we're gonna do two things, but this is the main focus is De Morgan's Law. So that's what I'm going to call my class. And so let's go ahead and get rid of our comments. Let's go ahead and put our main. I'm going to use a shortcut now. And there we go. And so the first idea is actually a really simple one. And we kind of do it automatically just because we can spot it and we're smart and smarter than computers in a lot of ways. And this is the idea of short circuiting. The idea of a short circuit is essentially when we have a logical expression, if, for example, in an AND, where the only time it's true is when they're both true. If the first statement is false, since we evaluate from left to right, in an AND, if the first statement is false, there's no need to look at the second statement because it doesn't matter what it is. If it was false, it would still be false. If it was true, the answer would still be false because the first one or the combination of the two would always end up being the same. Similarly, for the OR operator, the reality is if the first statement in an OR is true, then there's no need to look at the second statement because whether it's true or false, the whole thing is going to be true anyway. And so the idea of a short circuit is to kind of speed up the computer's calculation. Why look at the second half of a really complex statement if you don't have to? Right? So let's go ahead and write that. So short, right? Of a logical operator if value already determine, oh, excuse the noise, I don't know where that's coming from. If the value can already determine the result of the entire expression. So here we go. And so we've actually kind of seen it, but I'll go ahead and write one right now. Let's say Boolean short circ is equal to, and let's say something like 7 less than 5 and A greater than capital A. If I print this out, we can see what our result is. Now again, we can figure it out, but if we do what the computer does, and we look immediately to the first half, is 7 less than 5. It's false. So the reality is false and anything is automatically false. There's no need to look at the second half, and the computer wouldn't do it. It would save time. And the reason I bring this up is because in the future we're going to have certain very special conditions that we might ask, and if they're false, then we don't want to even look at the second one because it could cause problems. And similar with the or, if the first one is true, there's no need to even bother with the second one because it's good enough, right? Once it's true, the whole thing is true. And so short-circuiting is a strategy that computers take to speed up their determination of Boolean expressions. And so we can use that to our own advantage. And we should be able to spot when a computer will do it. In this case, the computer would never bother to check this second thing. Whether it's true or false, because the first one's false, the whole and is going to be false, right? So let's go ahead and try just a Boolean short circuit on or. So we'll say circ is equal to 15 2 equal to 1, or we'll say something like, I don't know, 32 divided by 5 less than 5. And again, the result is we don't care what the second half is because 15 divided, modulus 2 is 1, so this is true, so the whole statement is true. Whether the second half was true or false is irrelevant to the result of the or. The first one's true, the whole thing's true. The computer wouldn't bother checking the second half. And so we should get, I think, false and true as our output immediately for each of these. And again, can we see a difference? Not really, but the reality is the computer is doing less work, and that could definitely protect you. And we'll see when we do conditional statements that that's something that we use a lot. Right? Short circuiting is a very useful tool. Okay. So the last thing we're going to discuss is De Morgan's law, and this is a more formal written explanation. And I'm going to open up Paint so we can write this out directly. And essentially what we're going to say is that there's two rules that we need to know and how they apply to logic. If I have a statement A and a statement B, we know that in order to be true, both A and B must be true. Now, what De Morgan's law basically tells us is if we negate this entire operation, the question is, what is this equivalent to? And so De Morgan's law says that if you negate this is called a conjunction or the intersection, then the result is the same thing as the disjunction of the negations. Essentially what we're saying is if you negate an and, then that's the same as the or of individual negations. So if I were to do De Morgan's law, essentially it's kind of like distributing. You'd say distribute the negation to the A, distribute it to the and then distribute it to the second one, which is the B. And so the A and the B part are the easy ones. So this becomes not A, right? Because A negated is not A. The B is also easy. It's the question of what happens when you negate an and. Essentially what happens is we flip it. An and becomes an or. So this is equivalent to not B. Right? So we're saying the negation of A and B is equal to the negation of A or the negation of B. And so the same thing can be applied. The same thing can be said of the negation of a union or a disjunction. So if I say not A or B, what we're saying is distribute the negation, and then distribute the negation. And the result is not A. And then an or is flipped to an and not B. So the negation of A or B is the same as the negation of A and the negation of B, right? And the reality is we can go from either direction. And we can do more complex than this. Here I've distributed the negation inward. Technically speaking, we can pull out negations as well. And this relies on the assumption of one other rule, and this is just kind of a fact that I think is relatively obvious. If we have the statement A, we know that the negation of A is not A. But what is the negation of a negation? So if I say not A, what do I end up with? Not A. So if A is true, then the negation is not true, which is false, and the negation of false is true again. So what we can say is A is the same as not A. And I'm not putting the parentheses, but it's a double negation. And so essentially, if there's an even amount of negations, then you end up with the original statement. If there's an odd amount of negations, you end up with the negated result. And with this rule, then we can kind of take anything and pull this out. So for example, if I gave us the statement not A or B, then I could make, with De Morgan's law and with the fact that A is equal to not A, I could pull out a negation. I could say this is equivalent to. If I pull out the negation from not A, I end up with the A. If I pull out the negation from the or, that's the same thing as flipping it, so I'm going to make it into an and. And then since B is positive on its own, we can say B is the same as not B, and then now we're going to extract the one negation from it, and we end up with not B. So the negation of A or B, and so again, the way I say it is kind of important. So if the negation of A or B is the same as the negation of A and not B, right? They're equivalent, and if you think about how you pushed it in, it would end up being the same thing, right? We can come up with any combination, any number of statements, and ands and ors essentially flip when they're negated or when a negation is pulled out. But it's very much like the distribution and factoring that we might do. This is essentially what we're trying to do, is the equivalent of that. And this has a lot of applications because it essentially allows us to rewrite any logical statement that we think is easy to read in one way into another form, right? And this can be very, very useful. And we'll see that De Morgan's law is very applicable in a lot of situations because sometimes it's easier to write statements in a very positive way, right? Sometimes it's easier to write them in a negative way because that's what the kind of goal is, to be aware of a situation where something's not happening. And so rewriting something that says is happening to not happening, De Morgan's law allows us to do it in an accurate way. Unfortunately, if we tried to do the negations and we didn't flip the symbols, then it wouldn't really be the correct result. And that's something that we have to deal with. So De Morgan's law is very, very useful, and we can apply it in a lot of different situations, right? And we can kind of do this example. And so I'm claiming that these two statements are true, that they're equal to each other. So if I said in Java, not A or B equal to not A and not B, then we should get true, assuming A and B are set values. So let's try that. So here we go. I'm going to say Boolean A is equal to true. Boolean B is equal to false. And I'm saying it does not matter whether A or B are true or false. The result of these logical statements is going to be the same. And so I'm going to say Boolean part 1, or I could call it left, is equal to, and we said it was going to be not A or B. Boolean right is equal to not A and not B. And then now my question is, Boolean is same is equal to left equal to right. And I'm saying they're the same, so if we print out, I'm going to go ahead and print out a message as well, same. And then we can attach our is same variable. So let's see what ends up happening, right? And there they are, the same is true. Now again, if I had made the mistake of not flipping the symbol, so if I thought that this ended up being not A or not B, then this would not be the same. So if I had done this on accident, if I had misrepresented De Morgan's law and I ran it, we would see that they're not equal to each other. Oh, what did I do? Am I wrong? Not A or not B. Not A. Am I crazy, or did this end up happening? Ooh, what am I doing wrong here? Is same is left equal to right. Is same is assigned. Are they equal to each other? So if A is true, then we get not true. Oh, I guess it's possible. I guess it does depend on the actual values. No, that shouldn't be the case. Let's think about this for one moment. So I think that what we have to do to verify that this is not the same is we have to verify every situation. Right now, it's possible that because A is true and B is false, that they happen to be the same. But is that actual validation that they're the same in all cases? And this is something I haven't done yet, but we should do it. A truth table can easily validate all possible scenarios, especially because there are only two inputs. So let's try doing that. Let's make a truth table. Oops, I apologize. Let's make a truth table for these two statements. So here we go. So we're going to say we have the statement A. We have the statement B. We know that A can be true and A can be false. All right, so here we go. Apologize for that. And then now let's do this statement. So not A or B. That's one statement. And the other one is not A. And I'm actually not going to validate this one. I'm going to validate this one. So these two. So not A or not B. So the negation of A or not B. So here we go. In this case, B can be true or it can be false. And in this case, it can be true or it's false. So those are the four possibilities. So here we go. They're both true. Not true is false. False or true is true. It's true for A and false for B. Not true is false. False or false is false. Okay? False or true. Not false is true. True or anything is automatically true. And then A is false again. Not false is true. True or anything is true. So I can short circuit and not even think about it. So that's the output for this one. Let's look at the output for this one. And so here we go. True and true. True or anything is true. Not true is false. Okay, right there, they're different. So the claim is that if I switch A and B in the code to both be true, that we should not get a true like we did. True and false, right? So true or anything is true. True or anything is true, and not true is false. So they happen to match up here. So that's why I had used these two inputs, and so they look the same, and when I printed them, we thought they were the same, but they're not. And so how about now false and true? So false or not true is false, false or false is false, not false is true. So they match up there. And the last one, false or not false is true, false or true is true, not true is false. So there are two scenarios where they don't match up. Let's prove that this actually happens. So here we go. Right? I was using true and false, so that happened to be a situation where they matched up, so that's what confused me for a moment. Now let's try it differently. Let's go ahead and plug in two trues. And the claim, according to this truth table, is that they will not be the same. So is same should be false when we run this. And there it is. And so we cannot claim two statements are the same unless they give us the same outputs for every possible input. And so let's do the last one and see if it's going to be that false or false. So if we put them both to false, let's go ahead and run it and see what happens. False again. And let's do the one that they did. We said false and true. And we'll see that they might be the same. Right? There's no guarantee. It has to be for all four scenarios. Otherwise, they're not really equivalent, right? And so the same would apply. And if we did the truth table for these two, we would see that they would be the same in all four scenarios. And that's kind of a brute force proof of the De Morgan's law. And we could do the same for this one and for these as well if we needed to. We're going to stop here. We're going to continue our next video on a new topic, right? Where I think we're at the point where we can move on to something more interesting. And then the combination of all this stuff will get us ready to do our first big project. I'll see you in the next video.